Alright, welcome to the last page that we're going to do today, 8.22, where we have repeated eigenvalues. So nothing's really going to change in the way that we're actually finding our eigenvalues and eigenvectors. The only thing that's going to change here is when we write our solution. If we have repeated eigenvalues, then it could be set up very similar to when we had repeated answers for our differential equations. So suppose lambda sub 1 is an eigenvalue with multiplicity m, where m is less than or equal to n. There are two cases. All right. Sometimes it's possible to find m linearly independent eigenvectors corresponding to an eigenvalue, so lambda sub 1 of multiplicity m. Then the general solution will contain the linear combination x equals c sub 1 k sub 1 e to the lambda sub 1 t plus c sub 2 k sub 2 e to the lambda 1 t plus, and then goes all the way out to where we were able to finish writing all the different combinations that we could have for that eigenvector that corresponded to that eigenvalue. So usually this is the case when we have like k sub 1 is equal to negative k sub 2. And if we have something such as that, then we have, where we have different eigenvectors that correspond to different eigenvalues, right? That's the case that you're going to see here. The second case is if there's only one eigenvector corresponding to an eigenvalue, so our eigenvalue only gives us one eigenvector of multiplicity m, then m linearly independent solutions are given by, so again, this is if it's just one time. All right, or not. Well, this is if it's just two times. If it's just two times, then depending on how many roots that we need to take for that. So if it's a multiplicity 1, we have this. If it's a multiplicity 2, then you're going to have this as a solution plus, and then you're going to have that as a solution. So there's going to be a combination of x sub 1 plus x sub 2, and then you keep going until you finish how many times that it repeated. So if it repeated m times, then this is how you're going to set it up, not forgetting to add the previous ones to that. All right. So I'll give you an example of that in the homework, and then if you would like to see me do that, then tomorrow in class I'll do that for you. So example 5, we're going to find the general solution of the given system. And so we're starting off with 24. So this stinks because this is our coefficient matrix is going to be a 3 by 3. All right. So we're finding the determinant of that 3 by 3 matrix. So when we find the determinant, again, we set that up the same way. I'm not really going to go, just because I'm short on time before class is actually going to start. Here's the work for that. When we do the work, we realize, okay, that stinks because now I have, a polynomial with 3 terms, polynomial of degree 3, so I'm going to have to actually do synthetic division to help me find the zeros. When I find the zeros, I'm left with lambda equals 8 and lambda equals negative 1, but that negative 1 appears twice. So it's repeated. So now let's go ahead and now do lambda equals 8. If we do that, we plug it in, then we solve the system. When we solve the system, again, I'm not going to go too much into solving the system. We're going to get k sub 1 is equal to k sub 3, and if k sub 1 is equal to k sub 3, then we make k sub 1, k sub 3 equal 2. Then that's just going to give us for our k sub 2, 1. So we get 2, 1, 2. Again, we could have made that 4. If we could have made k sub 1 and k sub 3 both be 4, if we did that, k sub 2 would be 2. If we made k sub 1 and k sub 3 1, k sub 2 would be a half. All right, so you just need to make sure that, you get some combination of that, because, that eigenvalue is going to take care of that. So 2, 1, 2 is going to be our eigenvector. So there's our first solution. So I'll go ahead and I'll write that down. So our first solution is going to be, looks like I didn't write it down. It's going to be x is equal to C sub 1, our eigenvector 2, 1, 2, that corresponds to our eigenvalue 8t, plus C sub 2, and now we're going to do our negative 1. So we plug that in. When we plug negative 1 in, we're going to get the following system. Now we're going to solve that system. When we solve this system, realize, well, hey, everything is going to be equal. There's no way I'm going to eliminate any K sub 1 without, eliminating all of them. And so therefore we know, okay, well, we can set these up, we could say K sub 2 plus K sub 3, is going to be some value of K sub 1. If we did that, we'd say like K sub 1 is equal, or 2K sub 1 is equal to negative K sub, or 2K sub 3 plus or minus K sub 2. If that's the case, then we're going to find our different solutions. So we know that, hey, if I make, since, K sub 1 and K sub 3 are the same, have the same coefficient, then I'm just going to change both of those. So if I made K sub 1 be 0, then I'm left with 2K sub 2 for K sub 3. And then I can, if I do the same down here, I'm like, okay, well then I have K sub 2 plus 2K sub 3. And then I can go ahead and solve. I can find out, what value I'm going to make K sub 2 and K sub 3. Same thing if I eliminate K sub 3 and work with K sub 1 and K sub 2. So therefore, I found these two vectors that correspond 0, negative 2, 1, and 1, negative 2, 0, that are solutions to our system. So therefore, I have two different eigenvectors, and so now each eigenvector is going to correspond to my eigenvalue of negative 1. So plus C sub 2, we'll do 0, negative 2, 1. And then we have e to the negative t plus C sub 3 times the eigenvector 1, negative 2, 0, e to the negative t. And then there's our solution to that. Alright, again, it's going to take some work to do, but hopefully it's not too bad, because again, a lot of it's just algebra, and we're just, using matrix algebra to help us solve for a lot of